So, techniques for finding the complex roots of a number. That means that if you've got some number a and you want a particular root of it, what are these roots? And I've written z, of course. Z is the standard notation for a complex number. And a, I think to begin with, we'll just let a be a nice number, a nice little integer. Now, that would be the same as saying, well, if that's the nth root, then z to the power n will give this number. And one way of finding that would be, if I take that all over to one side and have z to the power n minus a equals 0, then I've got a nice wee polynomial that I could factorise to find the roots. And one thing you know from the fundamental theorem of algebra is that for a polynomial of degree n, there should be n roots altogether in the set of complex numbers. Some roots may be real, and the ones that aren't real would form conjugate pairs, so that together they would form a quadratic. But anyway, the main point is there should be n complex roots. Well, let's just start off with one. What about this? Z cubed equals 8. So if you were just to do that normally, you think, oh, well, what's z? Z will be the cube root of 8. That's 2 times 2 times 2. So that means there's an answer. Z equals 2. But that's the only one that comes out of that. Where's the other 2? I'm not going to get it from this. Z equals 2 is certainly one of them. But where are the other ones? Oh, I'll just have to go for my polynomial. Z cubed minus a equals 0. So I'll be factorising that then. Now there's a pattern for these difference of powers. If I just go back to ordinary x's, if I had something like x to the power 5 minus, we'll make it 1 to begin with, that factorisation would be x minus 1 times, and then all the powers below it. Simply because the minus 1 will knock off all the powers that x was producing apart from the very first one, and of course the very last one. And that applies to any number to the power 5. That would be a, but then that a would start to appear just to balance the powers. A squared, a cubed, and finally a to the 4. Now, of course, that applies to any of these powers. Any odd power follows that pattern. So, for this, I know that since that's 2 to the power 3, that will be z minus 2 times, then it'll be z squared plus 2 times z plus 4 equals 0. So that's the one I knew anyway, that was the 2. And this will give me 2 more by using the formula. So I've got z equals 2, that was fair enough, or z equals, now I've got to plod my way through this, negative b over the 2a plus or minus, and what's the discriminant? 4 take away 16 is negative 12. Oh, I've written it here, I'll have to put it down. That's negative 12. Now, that's 2 root 3 times negative 1. So this should be negative 2 plus or minus 2 root 3i all over 2. So finally I've got negative 2, no dot, negative 1 plus or minus root 3i. There's my 3 roots. A wee bit of working, but what's more interesting about them is if I now plot them in a diagram. If I plot them in an Argand diagram. Now, an Argand diagram is really just an ordinary coordinate diagram. In fact, those are the x and y coordinates of the point, where a complex number is written in the form of a real part plus an imaginary part. But the point is, x and y are real numbers. Which means along these axes, if you want to put in any scale points that refer to the x and the y, those would be numbers. Like that would be 1, that would be 2, that would also be 1, and that would be 2. Sometimes you get some confusion here between the scale points, which are the values of x and y, and indicating a complex number. So if I was to indicate the complex number 3, it would go there, and the scale point would be a 3, because strictly speaking, the coordinates of 3 are 3, 0. But if I was to put in the plot the complex number 3i, I could put a point there with a 3i beside it. That's perfectly correct. That's where 3i goes. It's just that on the scale there, it would only say a 3, because that's the point 0, 3. So it all depends how you want to show your complex numbers. Just plot them as points with the scales in, or don't put the scales in and just plot the actual numbers. So, where do these 3 roots lie on the Argand diagram? I'm not going to put scales in. In fact, I'll just call that the real axis and that the imaginary axis. So z equals 2 would be this number. 2 on the real axis, no imaginary part. -1 plus root 3 would be 1 back and root 3 up. That would be -1 plus root 3i. And similarly, -1 minus root 3i would be down here. Those numbers should ring a bell. 1, 2 and root 3. If I put in the radial lines leading to the points, or if you like the position vectors of those points, then for this one, that was 1 back and root 3 up. Recognise the triangle? That's the 1, 2, root 3 triangle. That's the same distance as that. So that's also 1, 2, root 3. So these are all the same distance from the origin. These complex numbers all have the same modulus. Is there something the same about their angles? Well, just sticking with degrees for this one, because I know my degrees quite quickly here. 1, 2, root 3 triangle's got a 60 in here. So that must be a 60. There's 120. If that's 60, that's 120. That's 120. They're equally spaced. In fact, these 3 roots are equally spaced in a circle of radius equal to the modulus of each of them. So this might be a route to getting the roots, if you can find just one of them. That would seem to imply once you've got one of them, just create a circle and then divide that circle into whatever the number is, number of roots, into that number of sectors, and there are your roots. Let's see if it works for the next one. Right, up for the next one then. I'll go up to power 4 for the 4th roots. I'll still stick with 2's though. You could also have 1's, but 1's are a bit more boring because they all look the same. Still, I know one of those answers. One of those answers is 2, because 2 to the power 4 is 16. And so will -2 be. So I know 2 of them, but what are the other 2? Well, let's just do it the polynomial way. So what's that? Well, there's the difference of 2 squares. So z squared minus 4. Z squared plus 4. That's the difference of 2 squares. Z minus 2. Z plus 2. Well, there are those 2 that I knew. And you can treat that as the difference of 2 squares as well. As in z minus 2i and z plus 2i. So the 4 roots, and with power 4 there should be 4 roots. That's 2, -2, 2i, and -2i. And I don't need the diagram to see that they're equally spaced, but here you are anyway. Notice that's showing the actual number 2i, not the scale point 2 for the value of y. So it looks like I could have done the same thing here. Once I know one of them, like 2, just create a circle, because all 4 roots have got the same modulus. Create a circle and then split it into 4 equal sectors from that first point, and there's your 4 roots. Looking good. Let's step it up to power 5 now. Still sticking with the 2's. But obviously I know that 2 works, but let's just go through this. What have we got? So that would be like solving the polynomial z to the power 5 minus 32 equals 0. Now I know that 2 works, so I've got that factor z minus 2, but I know that happens anyway, because that's z to the power 5 minus 2 to the power 5. So it will factorise to z minus 2 times z to the 4 plus 2z to the 3 plus 4z squared plus 8z plus 16 equals 0. Now I don't fancy that. I've got this quartic here, which will obviously factorise into 2 quadratics, but I don't want to go through all the jiggery-pokery of doing that. Right, well, I'm not going to bother with the polynomials anymore if they're going to behave like this. So there's another technique I could use. Since I'm using Argand diagrams in the first place, let's just switch back to that original and write this as a complex number in polar form. Now, if you want to write something as a complex number in polar form, you need its argument and you need its modulus. But the best way to get that is just to plop it onto an Argand diagram. There's 32, bang on that axis. So its modulus is obviously 32, being the distance from the origin, and its argument is 0, or rather, its principal argument is 0. Now there's something about arguments. To get the argument of a complex number, you measure the angle from the positive real axis anticlockwise. So we'll just say that angle was some number of radians. But the argument could be that, or it could be any number of complete turns on top of that, because they would always end up there. So plus n lots of 2 pi. Now that actually is the full argument of a complex number. The argument of a complex number is a multi-valued function. What's the point in that, you might say? Because they'll just end up at the same thing. But it was the same when you solved equations before. When you said, oh, sine x equals, I'll put this in degrees, sine x equals a half, you would say, ah right, x is 30 or 150. But it's not just that. It's 30 and 150 for both of them, plus any number of 360 that you care, because the sine function went on and on forever. So the answer for x went on and on forever. That was known as the general solution. And you would only shorten it to these two if you had a specific limit for x, if x only was permitted to have a certain interval. That's the general solution to a trig equation. That's, if you like, the general form of the argument. But back to that business. What's the point? Surely 30 degrees is the same as 390 degrees, insofar as they both go back to the same place. So if you looked away, you'd be none the wiser. Yes, but they're not the same if you divide them. If you divide them, you end up with totally different numbers. And that's what's going to happen here. So, that's the general argument for a complex number, written with a capital A. That's called the principal argument. And that's the one that lies between pi and negative pi. So in order to do this problem here of finding the complex roots, I'm going to write my number in polar form with the general argument. So for this one, I'll say that's equal to, well, the modulus is 32, and then that will be cos of the argument. Now it is 0, but I'll put 0 plus n lots of 2 pi plus I sine. Now it's getting annoying having to write all this out. 0 plus n lots of 2 pi. Now this is a pain in the neck writing all this out. I'm not going to be doing it much longer. And then to get z itself, you take the fifth root of the whole thing, so that'll be 32 to the power of fifth, and then it'll be this whole thing here to the power of fifth. But we'll just pop it down here and just say z, so it'll be that to the power of fifth and that to the power of fifth, which turns that into, oh, now that I've done that, I might as well pop this back down to a 2 now, turns that into cos, I know 0 doesn't make any difference, divided by 5 plus, I know I'm just spending a lot of time writing exactly the same thing again, haven't I? So I'm just going to abbreviate this. I'm going to abbreviate that to z is 2, and then the cos plus I sine, I'll just write a CIS of, and then the 0 won't make any difference, so I'll put n times 2 pi upon 5. So that's just a wee abbreviation to save a lot of time.
He's got that excited about using his CIS that he's forgotten to give Moivre the credit for letting us divide the argument by 5 there.
So where are all these roots? There should be 5 roots here. Well, you get the 5 roots by going through different numbers of n. So when n is 0, I'll get my first one. You could call it 1 if you like. I just like to call it 0 for like the original one. That'll be 2, CIS. If that's 0, it'll be 0, which is of course the number 2. 2 to the power 5 is 32. When n is 1, I'll have 2 CIS, 2 pi upon 5. When n is 2, I'll have 2 CIS. That'll be 2 times 2 is 4. But notice all you're doing is adding on another 2 pi upon 5. That's just like that diagram. They kept going forward by the same amount. Z3 will be 2 CIS 6 pi upon 5. How long can this go on? When n is 4, I'll have Z4 equals 2 CIS plus another 2 is 8 pi upon 5. Does that mean I can go to n5 as well? Because that's 6 of them now. Z5 is 2 CIS, because when it's 5 it will be 10. You say, oh wait a minute, 10 upon 5 is 2 pi, and 2 pi is just 0. I'm back to the start, so I don't need them. So those are the unique 5 roots. List them out. So I've got that one. Cos of 0 is 1, which would just be a 2. I knew that. Z1, you could either just leave it in polar form, 2 cos 2 pi upon 5 plus I sine 2 pi upon 5. Or you could put it back into Cartesian form by working out the cos of 2 pi upon 5 and the sine of 2 pi upon 5. And then of course the modulus times them both. And if you did that, you would get, because I've already done this, 0.618 plus 1.902i. And do the same for the rest, but you'd probably just leave them in polar form. But there is another one I know like this, because these two here aren't in the form of their principal arguments. If I was to write them in terms of their principal arguments, remembering pi upon 5, pi's halfway round, and that takes 5 steps. All the way around would be 10 steps. So that if I've gone 6 pi upon 5, I've gone beyond halfway, and that would be, I should really draw a wee diagram there instead of pretending you can see a little circle. If there was a little circle, and that was pi there, and I've split, notice, pi upon 5, I've split pi into 5 bits. So it would be the same down here. I know these bits aren't equal. So 6 pi upon 5 is actually here, beyond halfway, so that would be -4. That's just doubling the bottom because that's the number of bits. So 6 away from 10 is -4 pi upon 5, and 8 away from 10 is -2 pi upon 5. So I know that one as well, because that's just going to be the conjugate. This one will be 0.618 for the real part, but minus 1.902 for the imaginary part. But I don't think I want it in that form, I'll just put it back in this form. Z1 was 2 cos 2 pi upon 5 plus I sine 2 pi upon 5, etc. for the others. But what's more interesting is that they obviously are all equally spaced on a circle of radius 2 being the modulus. 5 equal sectors starting from 2, all 2 pi upon 5 apart. Another thing, of course, is if that is the 5th root of 32, then doing that to the power 5 should put you back to the 32. And of course, in terms of angles with de Moivre's, with angles in polar form, when you multiply, if you've got two numbers in polar form, R1, I'll just put CIS theta 1, and R2 CIS theta 2. If you multiply two numbers in polar form, then the modulus will be the product of the modulus, and the argument will be the sum of the arguments. That's how you use this in the first place. Multiplying a number by itself so many times just multiplies its angle so many times. But what I'm saying is, if that is the 5th root, then taking that through 5 times its angle should take you back to the original one, which of course was 32. But that must mean that if you start with 32, whatever direction it's in, and divide its angle, it should take you to the first root. But more, we'll try another one. So here's another one, up to power 6. We'll try it for a negative number this time instead of those positives. Well, first of all, what would that be in polar form? Well, where is -1? A quick little sketch of an Argand diagram. There's -1. What's its argument? Pi. Modulus, distance from the origin, 1. So it's 1, and I'm just going to put CIS, and that's pi, but put in the full argument plus n lots of 2 pi. That's the important thing when you're trying to find these complex roots. You'll have to put in the full argument, which means z will be 1 to the power of 6, well that won't matter, CIS, and then divide that by 6. So all over 6, but I think I'll take the pi out, and that will leave 2n plus 1 lots of pi upon 6. Maybe I could just have left the pi upon 6 there. So there should be 6 solutions. What's the first of them? Well, when n equals 0, z0 will be, now that's just a 1, maybe I'll not even show that, it'll just be CIS. When n is 0, it's just pi upon 6. z1 or z2, depends how you want to name them, do that yourself. When n is 1, that'll be 2 is 3 of them. Now I know that cancels down, but this helps the pattern going, because all that's going to happen each time is, well, when n is 3, the next one's going to be CIS. When it's 3, sorry, when it's a 2, I think that 3 caught my eye, when it's a 2, that'll now go to 5. But you can see what's happening. All that's happening is it's going up 2 at a time, which obviously means when I come to plot them, they're going in their equal steps of 2 at a time. So n equals 3, z3 equals CIS, 7 pi upon 6, n equals 4, CIS, now I'll go up to 9 pi upon 6, n equals 5, z5 equals IS, 11 pi upon 6. I can't get any bigger because 13 takes me back to 1, so that's my lot. There are the 6 complex roots of -1. Some of them can be simplified though. Let's just go through these. That's the same as pi upon 2. That equals CIS pi upon 2. So that's the number I. And that's 3 upon 2, isn't it? Or if you like, negative pi upon 2. So negative I. That can be simplified to its principal argument because it's gone beyond halfway. There was 12 bits. That leaves 5 going backwards. So negative 5 pi upon 6. That partners that one. And that's CIS, 11 away, means 1 backwards. Negative pi upon 6 to partner the first one. And on a diagram, there we are, just as expected. They've all got the same modulus of 1, and they're equally spaced about the first of them. Well, that was actually the first of them that popped out there, wasn't it? That first one popped out at an angle with an argument of pi upon 6. But after the first one, the rest are equally spaced about it with angles of 2 pi upon 6 of pi upon 3. So how could we maybe have got this then without any of that? Starting from -1, because remember, if they're the roots, then any of them, just take that one for instance, to the power 6 must pop you back out at -1. And of course power 6 means, in terms of arguments, if you multiply its argument by 6, it should take you to -1. And by the same token, if you divide the argument of -1 by 6, it should take you to the first of them. So we could have done that. We could have started with, there's -1, argument pi. So its first root would be, divide that by 6, pi upon 6. And having established that one, then rearrange my circle to line up with this and split it into 6 equal sectors. Now in the advanced higher exam, of course, if you're asked to find the complex roots of some number, this is what you'd put down. In fact, you might even have to tediously spell it out. Cos plus I sine, cos plus I sine. Don't jump in with this to get the answers. Otherwise, in some other situation, that's by far the quickest way to get the complex roots of a number. Just for the sake of completeness, here's another one, but I'm not going to do it, so don't worry, because they're all the same, aren't they? Here's another one, only this time I've gone for a full complex number. So how would you just start it off? Because I know what's going to happen with the answer. How would I start it off? Well, I'd get that in its polar form. 1 plus root 3, that's 1 along root 3 up. 1, 2, so that means its modulus is 2. This angle here, is 60 degrees, that's pi upon 3, so I'll write CIS pi upon 3, but don't forget, put in the full argument plus n lots of 2 pi. So then when I get z itself, it'll be 2 to the power of 7th, well that's a bit nasty, can't be helped. CIS, now it'll be this lot over 7. Now I need to tidy that up. If I've just put it here, if you've got pi upon 3 plus n lots of 2 pi all over 7, first thing I think I'd do is I'd multiply everything by 3, so that'll be over 21, and then that'll now become a 6. So you've got pi plus 6n, so that would be 6n plus 1 pi upon 21. But that just means you're going to start at pi upon 21 and then keep adding 6 onto that, so it'll be pi upon 21 plus 6, 7 pi upon 21, and so on. Or, just to finish it off, if I had to find the 7th roots of that, I could just start with that. 1 plus root 3, put the number in, there's the number 1 plus root 3i. I know the angle for that, that's pi upon 3, and I know the length for that is 2. And then I also know that I would divide the argument by 7 to get a root, because if I had a root I would multiply it by 7 to get there. So if I take this angle and divide it by 7, and I'd have to find the 7th root of 2 as well, unfortunately, this angle would come down to 1/7 of what it was. Let's just say it goes there. And of course I know what that is. That's pi divided by 3 divided by 7, that's pi upon 21 for this little bit. But that's easy enough to do. I take the argument and divide it down by 7, which gives me my first root. I then know that the rest of them lie on a circle of the same radius as that first root. And from this line to the first root, I'd split the circle into 7 equal sectors, starting from here. So something like that, where there's my 1, 2, 3, 4, 5, 6, 7 roots. Take the initial complex number with its radial line or its position vector, if you like, drawn from the origin, divide its argument down by the appropriate amount to find the first root, form a circle, and split that circle into that number of sectors to find the rest of the roots.